Hello everyone, welcome back. Today is going to be lesson 222, day 3, and I'm calling this the transformations of everything. All right, so this is where we put it all together. We've been studying so many different functions and really the same transformations just on different functions. We've got 6 of them that we've looked at so far. We've got the line, the quadratic, cubic, rational, square root, and absolute value. So our goals today are just to transform anything and everything that we see. Describe transformations, write the equation if we know the transformations, so forth and so on. So we should be able to handle any type of function. We should be able to handle going from graph to equation, equation to graph, or description to graph, whatever they throw at us, we should be ready for it now. Okay, so here we go. I created this table just as a quick study guide for you. This really encapsulates everything that we've been talking about for the last 2 weeks, and should be a very valuable thing just to kind of have by your side. And if I were a smart student, I would make sure that I have this when I'm taking my quiz. All right, because you can really use this as a reference so that you know, like if you have to write an equation, you have all the graphing forms in one place. If you have to look at a graph, you have all the different shapes right here so that you know which kind of function you're looking at. All right, so just kind of going through this table, you have the names of your different functions up here at the top, and then these graphs that I provided you are what we call the parent graphs. All right, so these are what these functions look like before we do anything to them. So before we reflect or stretch, before we move them up or down, left or right, this is what these functions look like before we've done anything to them. So this is in their original state. All right, something that didn't get drawn in, you might want to draw on are the locator points. So all of these functions have locator points that start at 0, 0. Okay, so if I were to go in, the locator point for this would be 0, 0, 0, 0. So when we see that parabola, the locator point is at the vertex. For the cubic, it's here at this point of inflection, but it's still on 0, 0. So if I run across a cubic that's been moved, I'm going to look for that little inflection point where it flattens out. Okay, the rational function, that locator point happens at the intersection of the asymptotes, which again occurs at 0, 0 before it's been moved. But if we encounter one that's been moved, we're going to look for the intersection of the asymptotes to figure out how it's been moved. Okay, the square root function, kind of hard to see here, but it does terminate here at 0, 0, and that is the locator point. That minimum of the square root function is the locator point at 0, 0. And then for the absolute value function, much like the quadratic, it's at the vertex here of the v. So that is our locator point there. And you'll notice for every single graph, it starts at 0, 0. And we use those locator points if we're ever given a graph and we have to figure out how it's been moved. Okay, so that locator point is really helpful in tracking down the left and right movement and the up and down movement. And I'll show you a couple of examples of that later on. All right, this next row tells us all of the parent functions. All right, so when we say parent function, I like to think of it as the easiest version of this type of function that we can think of. So it's the function before any of the transformations have occurred. So this is the most basic line there is. It's y equals x. This is before we add any a, h, or k values to the equation. Same thing here with the quadratic. The easiest parabola is y equals x squared. You'll notice a, h, and k not written in there because we haven't done anything to that parabola. So if I compare that to its graphing form down here, you'll see the a, h, and k values added into the equation, so that way you can see the difference. This is how it started. This is how it's going to look once we start doing stuff to it. All right, and you can kind of see those differences as we go through each function here. You can see them all side by side. The one that's really different is the rational function because of the fraction situation. All right, so when we look at that a, h, and k, that a takes the role of the numerator of the fraction. The h is going to go in the denominator with the x. And a big mistake that students tend to make with this one is they put that plus k in the bottom of the fraction. It's actually separate from the fraction. Okay, so don't make that mistake. Another one that students tend to mess up is the square root function, especially when they're doing the h and the k value. I'll see a lot of equations written with the k inside of the square root, but that k is outside of the square root. Okay, so make sure you exit the square root when you're typing your answer, and make sure that k is on the outside. All right, so that's a pretty good synopsis, just trying to go over the major points of that table, but to get more of the finer details, you'll need to go back through some of the older videos and watch when we discussed these functions in more detail. All right, now reflections do occur, right? And you can reflect any of these functions, and the way that you do it is you throw a negative in front of the a values into any of these graphing forms, okay? And you might want to go to Desmos and just type in, one of these parent functions, or create your own equation for one of these, and just experiment a little bit. Throw a negative in front of the a, see what it looks like after it's been reflected. The ones that students tend to struggle with are the cubics and the rationals when it comes to the reflections, because it's a little bit harder to see the reflection. They look very similar, but the reflections are a little bit more subtle than they would be like with the quadratic, which will open up downward. It's very obvious if a quadratic's been reflected because it opens up downward, but it's harder to see with the cubic and the rational. So I would highly recommend just going to Desmos.com and experimenting with your cubic and your rational to make sure that you understand the difference between one that has been reflected and one that hasn't. Okay, and this is just my quick little thing about locator points. They always start at 0, 0. Use those for your graphing problems. Okay, so let's do a couple of examples here. Right, so we've seen these problems before. I'm going to give you a verbal description. Your job is to write the equation. So you got to make sure you know what kind of function you're dealing with. Track your left and right movements. See if it's been stretched or compressed. See if it's been reflected. All right, so I'm going to start here with clue 1. It says it's a square root function, so I could go up to my table here and I could say, okay, well, square root function looks like this, so that's what my equation is going to look like when I'm done. So I'm just going to write down that blueprint. I always call them blueprints because it's a way, it's instructional on how to build our equation. All right, so I've got a times x minus h plus k, and that x minus h is inside of a square root. Now it tells me that the locator point is at negative 3, 4. So they're telling me my h and my k values by telling me the locator point, because I remember the locator point always starts at 0, 0. Okay, so if I have a locator point that's now at negative 3, 4, I know that it's been moved left and right, up and down. Okay, so to go from 0 to negative 3, it had to move left, and to move left I need an x plus 3. And I also know that the k value is going to be 4 because normally it starts at 0, so it went from 0 up to 4, so it went up 4, which means I need a plus 4 on the end. So I got 2 pieces of information from that one clue that they gave me in part B. Now it says it's been compressed by a factor of 0.2, so the stretch and compression factor is represented by A. So I would put a 0.2 in for the A value in front of my square root here, and then it says it has been reflected over the x-axis, and to reflect we have to put a negative in front of the A value. So that completes my equation. This takes into account everything that they described here. Okay, so let's try this one. This one says it is a line, and if I go back up to my table and reference the graphing form of a line, we have y equals a parentheses x minus h plus k. All right, so the line it looks a lot like the quadratic and the cubic. There's just no exponent up here. All right, so there's no power, there's no exponent, no 2, no 3. It's just a plain parenthesis. All right, and this one works a little bit differently than some of the other functions because instead of telling us about a stretch or a compression factor like they did over here, the stretch or the compression factor is the same thing as the slope of the line. All right, so in part B, they're telling us about the slope, and that slope is our stretch or compression factor. That's what we'll put in for A. So I'm going to say y equals, and I'll put a 5/3 in for A, and then it tells me that it contains the point for negative 7. Now it doesn't say that this is a locator point, but it doesn't matter because if you remember the lessons from the line, we can pick any point on the line as a locator point. Okay, so we can use this as our h and k values. All right, so remember when we go into the parentheses, it's opposite. So if this is a positive 4, I'm going to need a minus 4 here. And then on the outside of the parentheses, it stays the same. So I can just put a minus 7 on the end. And that completes my equation here for this line. Okay. All right, this one's almost the same thing. It's just instead of a verbal description, they actually just give you a picture of the graph, okay? So you have to go into the graph and you have to find the information that you need. So one of the first things you're going to want to look at is the shape of the graph, right? So this has a very peculiar shape, and you might go back up to your table and look for that same shape here. And I noticed that it looks a lot like this one, which is a cubic function. And I'm looking at my graphing form down here for a cubic, so now I have the blueprint for my equation. So I'm going to come down here and I'm just going to write out my blueprint, and then I can start looking for my AH and K values. So I'm going to say y equals a parentheses x minus h cubed plus k. All right, so this is what my equation is going to look like. All right, so here we go. Let's start with the stretch or the compression factor. In all of these problems I've ever given you, you can always assume, if it's a graphing problem, like where we go from a graph to the equation, you can assume that the stretch factor is either 1 or -1. Okay, so all you have to determine is whether or not it's been reflected or not. So, and like I said, with cubics, that can be a little difficult. So what I do is I go to the locator point, and as I go to the right, I notice this thing is going up. Okay, if this had been reflected from the locator point, it would go down if it were reflected. Okay, so this one is going up. So it's telling me that it's not reflected. The other way that I could do it is I like to go to the parent graph and I look at its direction, right? So the direction is the same. It's going up and to the right, down and to the left. And remember, the parent graph is what it looks like before anything's been done. So I know this has not been reflected, and I can compare the directions on either end to what I have in my graph, and it's going up and to the right and down and to the left just the same way. So it has not been reflected. So I'm going to say y equals 1, just a regular 1, not a -1, because it hasn't been reflected. The next thing I'm going to look for is my locator point, and remember the locator point is located here at this point of inflection. So this is my locator point, and it's located at 3, 2. So normally the locator point starts here, so it had to move to the right 3. So to move to the right 3, I would do x minus 3 cubed, and then it went up 2. Okay, so to move up 2, I would do plus 2. And that completes my equation for that cubic. All right, let's do it one more time. This time let's take a look at the shape first. This is that distinct V shape, and if you reference your table up above, you'll remember that this is an absolute value function, and the graphing form for an absolute value function looks like this. So we have a absolute value, x minus h plus k. And remember, the stretch factor in these types of problems is always going to be 1 or -1. And the absolute value, it's really easy to see if it's been reflected because it'll either open up, it'll be an upward V, or it'll be a downward V. And if it's a downward V like this one, it's been reflected. So we can say -1 for our A value. And then I'm going to go find my locator point. And so the locator point is at the vertex of the V, so it's located right here. And remember, locator points usually start at 0, 0. So this one has been moved, and I need to track left and right, up and down. So I'm going to start with the left and right to get my h value. So I'm going from 0 to the right 1. So to move right 1, I need an x minus 1. And then it goes down 2 to get to -2 here. So I'm going to go -2 for the k value. And that completes my equation for that one. Okay. All right, last two examples I'm going to show you here. It says describe the transformations given an equation. So you have the equation. You're not writing an equation anymore for this one. Instead, you just need to verbally tell me what the transformations are just by looking at the equation. Okay, if it helps you, you can graph it. You can get on your calculator and graph this thing and take a look at it, and sometimes looking at the graph makes it easier to see the transformations that have taken place. But the goal here is to be quick and efficient, right? So I don't want you doing any more work than you have to, so you should be able to see the transformations just by looking at the equation, but if you need the graph, go ahead and use it. Okay, so I like to work from left to right, and every little piece of the equation does something to this. So first thing I'm going to describe is what kind of a function is this. And I notice that it has a 2 here, so it's quadratic. So this is a quadratic function. This is going to make a parabola on the graph, right? And then I go here, okay, I say, well, there's a negative out front of the A, so it's been reflected. And that negative in front of the A is always going to reflect over the x-axis. Okay, so I'm trying to be specific about where it reflected as well. Now the 1/2, right, that 1/2 represents either a stretch or a compression factor. Since the 1/2 is a number in between 0 and 1, it has been compressed. If it's anything bigger than 1, it would be a stretch factor, but this is a compression factor since it's in between 0 and 1. So this has been compressed by a factor of 1/2. Okay. All right, then I move over here to the 5. This -5 shifts right 5. Remember, it's opposite of what you think it would do. A -5 moves to the right, a +5 would move to the left. Okay. And then moving along here, I got a -6 on the end, so that means it shifted down 6 units. And I forgot to write my units up here, so it shifted right 5 units. And there we go. That would be a good description of what happened to this parabola. All right, let's try it one more time. We'll start with this one. Remember, if you're looking at it and you're not sure what kind of a function it is, compare your function to the graphing forms that you see in your table that I gave you. This one should look a lot like a rational function. So I'm going to start off by just describing that it is a rational function. Okay. And we'll start with the 3 up top. So in the graphing form of the rational function from our table, this is where the stretch factor would go, or the compression factor. And since the A value is a 3, that's bigger than 1, so this is vertically stretched. So vertically stretched by a factor of 3. Okay. And then I go down here, I have this -4. This is where our H value would be. So this is our horizontal transformation, or translation, I should say. So a -4 would indicate that it has been shifted right 4 units. Okay. And then I take a look at the +5 here. That's where my K value would go. So this is telling me that it's been shifted up 5 units. There we go. And I noticed one thing I'm missing from this one that was over here was a reflection, but I don't see a negative in front of the A. So no reflection happened, so I don't need to talk about it in my description. Okay. All right, guys, that's it for today's video. Hopefully you found that helpful. If you have any questions, please let me know in the Zoom chat. Have a great day.